Right here in chat. Enjoy the script. You are touching nothing right now. Not the chair beneath you. Not the phone or keyboard in your hands. Not even the ground beneath your feet. Every sensation of solidity, every feeling of contact, is a magnificent illusion. A trick played on you by invisible forces operating at a scale so small it defies imagination. And once you understand what's actually happening, you will never look at the physical world the same way again. Welcome to the hidden physics of everyday life. Richard Feynman once said that the world is far more subtle than we give it credit for. He wasn't being poetic, he was being precise. Because beneath every ordinary moment, a campfire crackling, a hand touching a table, a light bulb switching on, there is a universe of staggering complexity and breathtaking beauty operating in plain sight. We just haven't learned how to look. That's what we're doing today. We're going to look, really look. Let's start with something primal, something humans have gathered around since before recorded history. Fire. What fire really is. Stored sunlight breaking free. Watch a candle flame. Just watch it for a moment. What are you actually seeing? Most people would say burning wax, combustion, heat and light. And they'd be right, in the same way that saying the Mona Lisa is paint on wood is right. Technically accurate, completely missing the point. Here is what fire actually is. Millions of years ago, or in the case of your candle, just a few years ago, sunlight struck a living thing. A tree, a plant, a colony of ancient marine organisms. That sunlight carried energy, pure electromagnetic energy that had traveled 93 million miles from the surface of the sun. When it arrived, something extraordinary happened. A plant absorbed it. Using the miracle we call photosynthesis, that plant took the energy of sunlight and locked it, chemically imprisoned it, inside molecular bonds. Carbon atoms linked to hydrogen atoms, hydrogen to oxygen, in long, intricate chains we call hydrocarbons. The plant died. Maybe it became coal over millions of years of geological pressure. Maybe it became the paraffin wax in your candle, refined from ancient petroleum. Maybe it simply became a piece of firewood sitting on your hearth. And there it waited. That sunlight, that energy from a nuclear furnace 93 million miles away, sat patiently locked inside those molecular bonds, sometimes for millions of years, sometimes just a few decades. Waiting. Then you struck a match. What happens next is almost violent in its elegance. The heat of the match provides just enough energy to break those first molecular bonds apart. Oxygen from the air rushes in. The carbon and hydrogen atoms, now liberated, combine with that oxygen in a process that releases all that stored sunlight. In a cascade of molecular collisions happening billions of times per second, the imprisoned solar energy from long ago breaks free. It becomes heat. It becomes light. It becomes the dancing, flickering glow of a flame. Fire is not creation. Fire is liberation. You are not making energy when you burn something. You are releasing sunlight that was trapped, sometimes before your grandparents were born, sometimes before the dinosaurs walked the earth. Every campfire is a delayed sunrise. Every candle is ancient starlight coming home. Stop. Think about that for a moment. The warmth on your face when you sit by a fire? That is the sun touching you. Not the sun that's up in the sky right now. The sun from years, decades, sometimes millions of years ago. Time travel of a kind. Delivered to you by chemistry. But here's where it gets interesting. Because fire is dramatic, visible, easy to marvel at. What about something quieter, something invisible? What about heat itself? The atomic dance. What heat actually is right now? The coffee cup on your desk, or the table in front of you, or the air in your room. Everything around you is alive with motion you cannot see. Every piece of matter you have ever encountered is made of atoms. You already know this. But knowing it intellectually and feeling it viscerally are two very different things. So let's make it visceral. Imagine you could shrink down, not to the size of a bacterium, not even to the size of a virus. Much smaller, down to the scale of molecules. And now imagine you're looking at what appears to be a perfectly still, perfectly solid wooden tabletop. It isn't still. It isn't even close to still. Every atom in that table is vibrating. shaking, jostling, rattling back and forth in place, with an energy that never, ever stops as long as the temperature is above absolute zero minus 273 degrees Celsius, the coldest temperature physically possible in the universe. At room temperature, atoms are vibrating roughly 1 trillion times per second. 1 trillion times per second. That table that looks so passive, so inert, so boringly solid, it is a riot of invisible motion. A symphony of atomic vibration playing continuously, ceaselessly everywhere around you. And here's the key. That vibration is temperature. Temperature is not something that atoms have. Temperature is something atoms do. When you put your hand near a hot stove, what's happening? The atoms in the stove are vibrating violently. They have a lot of vibrational energy. The atoms in your hand are vibrating more gently. When they get close enough, those fast-moving atoms start bumping into the slower atoms of your hand, transferring their motion. Your hand's atoms speed up. They jostle the atoms next to them. A wave of increasing atomic motion propagates through your skin, through your nerve cells, and your brain interprets that wave of atomic excitement as the sensation of heat. Heat is contagious motion. Temperature is the enthusiasm of atoms. Now, you might be thinking, okay, but solids vibrate in place, right? What about liquids? What about gases? This is where the picture gets even richer. In a solid, atoms are locked in a kind of crystalline embrace. They vibrate, but they stay in their positions, like people in a crowd swaying but keeping their feet planted. In a liquid, atoms have enough energy to break some of those bonds and move around each other. Now it's like a mosh pit, still densely packed but flowing. In a gas, atoms have so much energy they fly completely free of each other, zooming across entire rooms, bouncing off walls and each other at hundreds of meters per second. The water in your kettle starts as a solid at 0 degrees Celsius, atoms locked in hexagonal crystalline patterns, which is why snowflakes have six-fold symmetry, incidentally. Raise the temperature and you melt those bonds, freeing the atoms to flow. Keep raising it and you eventually give those molecules enough energy to escape the surface entirely, flying off into the air as steam. You didn't add wetness or steaminess to the water. You added motion. You sped up the atoms. Everything else, the phase changes, the state of matter, is just what happens when atoms collectively have different amounts of dance in them. Feynman described this once with characteristic joy. He said that if you had to communicate the most important scientific knowledge to the next generation in just one sentence, it would be this: all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. Attracting when apart, repelling when squeezed together. That second part brings us to the most mind-bending revelation of all. "You never touch anything here" is a statement that sounds insane and is completely true. You have never touched anything in your entire life. Not once. Not a single time. Your hand resting on your leg right now. Your feet on the floor. The feeling of fabric against your skin. None of it involves actual contact between matter. What you experience as touching is electromagnetic repulsion between electron clouds. Let's unpack that. Atoms are almost entirely empty space. You've probably heard this. The nucleus of an atom, the dense central core containing protons and neutrons, is unimaginably small compared to the overall size of the atom. If an atom were the size of a cathedral, the nucleus would be a grain of sand sitting in the center. The rest of the cathedral, all that vast empty space, is where the electrons live. But electrons don't just orbit the nucleus like tiny planets, the way old textbook diagrams suggest. They exist as probability clouds, quantum mechanical hazes that surround the nucleus, spending more time in some places than others, but never truly sitting still, never occupying a fixed position. These electron clouds extend outward from the nucleus and define what we think of as the surface or size of an atom. Now, when two atoms get close to each other, their electron clouds begin to overlap. And here's the critical thing. Electrons all carry negative electrical charge. Like charges repel each other. So when electron cloud meets electron cloud, an electromagnetic force pushes them apart. This repulsion is what you feel as solidity. When you press your finger against a table, the electrons in the outer atoms of your fingertip are getting close to the electrons in the outer atoms of the table's surface. They repel each other. Your nervous system interprets that electromagnetic push as the sensation of touch, of hardness, of solidity. But the atoms themselves, they never make contact. They get close, extraordinarily close, separated by distances of about an angstrom or a 10/1000th of a meter, and then the electromagnetic force says, no further. Imagine two powerful magnets, same poles facing each other. Push them together and you feel resistance, real, tangible resistance, even though the magnets never actually touch. The force is real, the solidity is real. But contact? There is no contact. That is exactly what's happening when you touch anything. The floor is holding you up not because it's solid in any classical sense, but because its electrons are refusing to let your electrons pass through. Gravity pulls you down. Electromagnetism pushes back up. You float, perpetually, on an invisible electromagnetic cushion, a nanometer above every surface you've ever touched. Sit with that for a moment. You are not sitting on your chair. You are hovering above it, suspended by the repulsion of electron clouds, and your nervous system has been lying to you your entire life about what that feels like, how electricity actually flows, and why your textbook was wrong. Here's another one. You learned in school probably that electricity is electrons flowing through a wire, like water through a pipe. You flip a switch, electrons race through the copper from the power plant to your light bulb, and light happens. This is not quite right. And the true picture is far stranger and more beautiful. Yes, electrons move through copper wires when you have an electric current. But here's the first surprise. They move incredibly slowly. We're talking about drift velocities, the average speed at which electrons actually travel through a wire, of roughly 1 millimeter per second, sometimes slower, 1 millimeter per second. And yet when you flip a light switch, the light comes on essentially instantaneously. The electricity doesn't have to arrive from the power plant. So what's happening? Think of it this way. Imagine a long pipe completely filled with water. Not an empty pipe, a full one. You push water in one end. What happens? Water comes out the other end almost immediately, even though the specific water molecules you pushed haven't traveled anywhere yet. The pressure propagates through the entire filled system at the speed of sound in water. Electricity works similarly, but with electromagnetic fields instead of pressure. The copper wire is already full of free electrons. Copper is a fantastic conductor precisely because each copper atom donates roughly 1 electron to a shared sea of electrons that can move freely through the metal. When you connect a circuit, you don't send electrons racing from one end to the other. Instead, an electromagnetic field propagates through the space around the wire at close to the speed of light, and that field pushes all the electrons in the wire simultaneously, just a tiny bit, all at once. The energy doesn't travel through the wire. The energy travels through the electromagnetic field surrounding the wire. The wire itself is more like a guide, a shape that constrains and directs the field. This has a remarkable implication. When you turn on a light, the energy that lights the bulb didn't come racing through the copper just now. It was transmitted through the electromagnetic field in the space between and around the wires, effectively instantaneously on human timescales. The electrons in the wire do the minimum amount of shuffling necessary to sustain that field. They're more like the banks of a river that direct flow than like the water flowing itself. Physicists Poynting and Maxwell worked out the mathematics of this in the 19th century, and the result still startles students when they first encounter it. In a wire-carrying current, the energy flow is actually perpendicular to the wire, passing through the surrounding space, not through the metal itself. Now you might be thinking, but the wire gets hot when it carries a lot of current, so surely something is happening in the wire. Yes, absolutely. Resistance. The electrons, shuffling along, do collide with atoms in the metal, transferring energy to them, speeding up their vibration. And what's atomic vibration? Temperature. Heat. That's exactly the atomic dance we talked about earlier, now understood in a new context. The heat in a resistor is electron energy being converted to atomic motion. But here's where it gets interesting. All of this, all of electromagnetic theory, all of what Faraday intuited and Maxwell formalized, is, at its deepest level, a consequence of quantum mechanics. Which brings us to the extraordinary fact that quantum physics isn't just for particle accelerators. Quantum mechanics is happening in your kitchen right now. The word quantum has become synonymous in popular culture with mystery, weirdness, and inaccessibility. Quantum computers. quantum leaps. Things that happen at the bleeding edge of science in laboratories cooled to near absolute zero. But quantum mechanics is operating right now in the most mundane places imaginable. Your kitchen toaster uses quantum mechanics. So does the metal of your car. So do your bones, your DNA, and the nuclear reactions in the sun that will eventually, perhaps, end up warming your face around a campfire. Let's start simple. Why are some materials conductors of electricity and some insulators? Why does copper wire carry current happily while rubber stops it cold? The answer is quantum mechanics. Inside any solid material, the electrons don't have access to just any energy level they want. Because of quantum rules, specifically, the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously, electrons arrange themselves into bands of allowed energies, separated by gaps of forbidden energies. In a conductor like copper, the highest occupied energy band is only half full. Electrons at the top of this band have lots of empty states just above them that they can easily jump into. Apply a voltage, push on the electromagnetic field, and electrons can accelerate up into those empty states, moving through the material. Current flows. In an insulator like rubber, the highest occupied band is completely full, and the next available band is separated by a large energy gap. There's nowhere for electrons to go. No current flows. In a semiconductor like silicon, the gap is smaller. Under most conditions, electrons can't jump across it. But add a little heat, speed up the atomic dance, or shine light on it, and some electrons gain just enough energy to leap the gap. Current trickles. And by carefully engineering these materials, by adding impurities atom by atom, by layering them in precise configurations, we can control exactly how and when that current flows. That is the transistor. That is the microchip. That is every smartphone, every computer, every piece of digital technology on Earth. A transistor is a quantum mechanical device. Your phone is running on quantum physics, not the exotic theoretical kind. The practical, engineered, utterly mundane quantum physics of electron energy bands in crystalline silicon. Now here's a thought experiment that Feynman might have loved. Imagine you're looking at a piece of iron, a lump of it, gray, heavy, unremarkable. Nothing about it, to casual observation, suggests anything exciting is happening inside. But inside every iron atom, electrons are spinning. Not spinning the way a top spins. Quantum mechanical spin is more abstract than that, a fundamental property of the electron itself that has no classical analogy. But the effect is real. Each spinning electron creates a tiny magnetic field. In most materials, these tiny magnetic fields are randomly oriented, pointing in all different directions, canceling each other out. The material is not magnetic overall, but iron is special. In iron, quantum mechanical forces cause neighboring electrons to align their spins. Little regions form, magnetic domains, where all the electrons are pointing the same way, and so the entire domain acts like a tiny magnet. In an unmagnetized piece of iron, these domains point in random directions, canceling out. But drag a strong magnet along it, and you force the domains to align. Suddenly, the whole piece of iron is magnetized. That refrigerator magnet holding up your grocery list, that is quantum mechanics on display in your kitchen. The magnetic force that allows it to cling to your refrigerator door, that emerges directly from the quantum mechanical spin of electrons, aligned by quantum forces into cooperative domains, producing a macroscopic force you can feel with your finger. The world, it turns out, runs on quantum physics from top to bottom. It's just that most of the time, the quantum effects are averaged over so many trillions of atoms that they produce ordinary-looking, classical-feeling results. Touch enough quantum weirdness together and it starts looking like a table. The profound implication. What this all means. Let's come back to where we started. You are not touching your chair. You are hovering on electromagnetic repulsion. The warmth in the room is atoms dancing. The light from your lamp is energy flowing through electromagnetic fields, guided by quantum mechanics in crystalline silicon, ultimately traced back to nuclear fusion happening in a star 93 million miles away. Your very sense of solidity, of being in a physical world of hard surfaces and tangible objects, is the macroscopic consequence of quantum rules governing particles so small that billions of them would fit in the period at the end of the sentence. Everything is far stranger than it looks, and that strangeness is not a defect in the universe, it is its greatest feature. Richard Feynman used to describe the experience of really understanding science as like this. It's like being given a key that opens not one door, but an infinite corridor of doors. Every answer reveals 10 new questions. Every explained phenomenon opens a window onto a dozen unexplained ones, and the questions get better and more beautiful the further you go. He was right. Of course he was right. Because here is what's extraordinary about all of this. The physics we've talked about today, fire, heat, touch, electricity, quantum mechanics, this isn't cutting-edge research happening at CERN or MIT. This is the physics of your kitchen table, of your coffee, of your hands. It is happening everywhere, all the time, whether or not anyone is paying attention. The universe is not waiting for scientists to notice it doing something remarkable. It is doing something remarkable constantly, in every cubic millimeter of space, in every moment. We just spent most of human history not having the right questions to ask. Now we have some of them. And here's the most human thing about all of this. When Feynman explained physics, he wasn't just trying to transfer information. He was trying to transfer an experience, the experience of seeing the world as it actually is and finding it more magnificent than the simplified version we were raised to believe in. The fire isn't just fire. It's imprisoned sunlight escaping. The solid table isn't solid. It's an electromagnetic illusion. The light switch isn't just a switch. It's a command that propagates through fields at the speed of light, mobilizing quantum mechanical electron seas in crystalline copper, delivering energy that was generated by turbines spun by steam, which was boiled by burning fuel that is ultimately stored solar energy. The same energy, the same sun, that warmed the oceans where the first life on Earth learned to photosynthesize and lock sunlight into molecules for the very first time. We are not separate from the physics. We are made of it. Every atom in your body was forged in a star. Every electron you're reading with right now has been around since near the beginning of the universe. You are the universe, shaped by 13.8 billion years of physics, looking at itself and just starting to understand what it's made of. That is not a small thing. That is the most extraordinary thing imaginable. So the next time you sit by a fire, feel the heat on your face and remember that is sunlight. Ancient sunlight coming home. The next time you touch a table, remember you aren't touching it. You're repelling it, floating above it on an invisible electromagnetic field. The next time you flip a light switch, remember you are commanding quantum mechanical processes in crystalline silicon to redirect electromagnetic fields through space. You are surrounded, always, by miracles that have been operating since long before anyone had words for them. All it takes to see them is the willingness to ask what's really going on, and the patience to be astonished by the answer. If today's journey into the hidden physics of everyday life left you seeing the world a little differently, that's the whole point. Physics isn't a subject. It's a lens. And once you put it on, the ordinary world never looks ordinary again. Explore more. Ask more. The corridor of doors is long, and every single one of them opens onto something beautiful.